site. Please let me know, dear students, through your comment you're getting the audio video stream properly. Yes, Ritan, Shruti, good evening, beta, good evening. Good evening, dear students. I hope everybody doing well and good. And I also hope audio video is clear from my side. Please let me know, dear students, through your comment you're getting the audio video stream properly. All right. Yes, Ritan, Shruti, good evening, beta, good evening. Yesterday we did some discussion on BJT acting as an amplifier and switch, and we learned that BJT can be in these three regions: cutoff, active region, and saturation region. We have seen these graphs yesterday. We plotted these graphs yesterday, and in these graphs I told that region 1 is cutoff, students, where I hope BJT will act as an off switch, well and good. Then region 2 is and I also hope audio in video that saturation region side collector current is please remaining constant, students, through even if you increase or decrease the audio video stream properly. Okay, that IC will be constant here irrespective of VI, whereas in region 3 that we call as an active region, and in this region 3 collector current will vary according to some discussion on in input. BJT acting as an amplifier and switch active region, and we learned and that relation IC equal to beta IB can be, it will be applicable regions for this active region, and saturation region. As we keep on increasing VI graphs yesterday, base current will increase this graph, and collector current will keep on and increasing graphs. I told up the region IC side, students, where collector current BJT will doing as off IC side, well and good. Then this region 2 is where the current is becoming constant saturation. That region we called collector current is remaining constant, students, through even if you increase you want, you can show it in the video stream properly. This particular point, the IC will be constant here, becoming constant of this particular point, whereas in region 3 that we call as an active region, and in this region 3 collector current will vary according to some discussion on saturation. BJT acting as an amplifier and switch active region, and we learned and the point relation where IC collector current is becoming constant applicable we can call for this onset of saturation and onset means as we keep on increasing the saturation. Yesterday base current will be your active region and collector current will, and then keep on increasing of saturation. I told up the region onset of saturation where collector current will be how much of IC side, well and good. Then this point onset where saturation is becoming IC becomes saturation IC called collector current. Please the remaining students BJT will you satisfy or you can IC audio video stream properly. This particular point the IC onset of saturation becoming constant of this particular point, whereas in region 3 that we call as an active region. IC approximately equal to beta IB is valid in active region, valid in active region up to onset of saturation, up to onset of saturation. So this is one extra point which I wanted to convey to you all. IC approximately equal to beta IB, this relation will be valid for active region up to onset of saturation, and once BJT goes into saturation, that relation IC equal to beta IB will be invalid. So please copy this point. And if you consider that onset of saturation, at that onset of saturation IC will be IC sat. Okay, so let me also write this point. at onset of saturation if I want to know base current, I want to know how much is base current at the onset of saturation, I can apply IC equal to beta IB relation, put IC as IC sat. Okay, so I will get from there IB equal to IC sat divided by beta. Remember, IC equal to beta IB is applicable up to onset of saturation. At that onset of saturation, IC is how much? IC sat. So you just put IC equal to IC sat, you will get IB equal to IC sat divided by beta. So remember, this is nothing but your base current at the onset of saturation. When saturation begins, at that moment IB will be how much? IC sat divided by beta. So in the exam, they can ask you a question in this way also. Calculate base current in the circuit shown when BJT is at the onset of saturation. Okay, question can be asked in this way. Calculate base current in the circuit shown when BJT is at the onset of saturation. Please copy this formula. I hope the audio issue is clear now. All right. So I was telling you this point that in this graph, this particular point is called onset of saturation. Okay, the point from where IC becomes constant, it can be called onset of saturation. And BJT will satisfy that relation IC equal to beta IB for active region and up to onset of saturation. Please remember this point. Okay, IC approximately equal to beta IB, it will be applicable for active region and up to onset of saturation. And at that onset of saturation, if I want to know how much is IB, then I can use that relation IC equal to beta IB, put IC as IC sat, then you will get IB equal to this much. So this is base current at the onset of saturation. In the exam, they can ask question about this also. In the BJT circuit shown, calculate base current when BJT is at the onset of saturation. Okay, that current will be this much. And once BJT goes into saturation, IC will remain IC sat, but IB will keep on increasing with the input. That's what we learned yesterday, right? When BJT goes into saturation, IC will become constant at IC sat, but IB will keep on increasing with the input. If you increase input, IB will keep on increasing. IB will become more than this when BJT goes into saturation. Is that fine? So this is one extra point that you should keep in mind. And we will now proceed to our next topic. Our next topic is how to find operating region. let us make a heading, procedure to find operating region. Procedure to find operating region of BJT. This is an important topic from where questions have come in the GATE as well as ESC paper. You will be given one BJT circuit and you will be asked to tell in which region BJT is operating, whether BJT is in cutoff, whether BJT is in saturation, or whether BJT is in active region. Now to find this operating region, there are two possible methods. There are two methods to find the operating region. I call them method 1 and method 2. I will teach you here both methods. In the exam, you can apply any method, it is up to you. First, we will go through method number 1. You can take method 1. Now in this method number 1, there are 4 steps to find operating region. When we apply method 1, we have to follow 4 simple steps. You can note down these steps. Step number 1. Step 1. In step 1, we assume BJT in saturation. Assume BJT in saturation region. We start with this assumption that BJT is in saturation region, and when BJT is in saturation region, you have to take VCE equal to VCE sat. Okay, we studied yesterday, when BJT is in saturation, VCE will be how much? VCE sat. And I have also given you the value of VCE sat. How much is VCE sat? VCE sat is 0.2 volt for silicon transistor and 0.1 volt for germanium transistor. Okay, and there is one more value that we need to keep in mind, VBE sat. VB will be equal to VBE sat. When BJT is in saturation, VB is equal to VBE sat. VB saturation. Now this VB saturation, it is 0.8 volt for silicon transistor and 0.3 volt for germanium transistor. Okay, when we assume BJT in saturation region, we take VCE equal to VCE sat and VB equal to VB saturation. Now this VB saturation, it will be given in the question. Okay, VB sat, it will be provided in the question, whereas VCE sat, it may be given, it may not be given. So you have to remember VCE sat value 0.2 volt and 0.1 volt. VB sat, it will be given in the question. Okay, and all these values, they are for NPN transistor. If it is a PNP transistor, then these voltages will be negative. Okay, I have written these voltages for NPN transistor. If it is a PNP transistor, we should take these values minus, negative, minus 0.2, minus 0.1, minus 0.8, minus 0.3. Okay, you can note that point also. Please copy this step. And you can note down this point also. For PNP transistor, above values are negative. For PNP transistor, above values are negative. Okay, so if you get a question with PNP transistor, then remember these voltages will be negative for PNP transistor. Values remain same, only sign will be different. NPN transistor, these voltages are positive, and for PNP transistor these voltages are negative. So this is our step number 1. Okay, then you can take step number 2, second step. Step 2, calculate IB and IC. Calculate IB and IC. This will be our second step. Calculate IB and IC independently. When I say independently, I mean we should not apply that relation IC equal to beta IB. Okay, you should find IB IC without using IC equal to beta IB. That IC equal to beta IB, it is applicable for active region, but here we have assumed BJT in saturation, so we cannot apply IC equal to beta IB. Without using IC equal to beta IB, you should find IB and IC. That I call as independent calculation. So this will be the second step. Then step 3. In the third step, we will calculate minimum base current for which BJT remains in saturation. You can take the third step. In the third step, we will find out minimum IB required to operate BJT in saturation. Find minimum IB, minimum base current required to operate BJT in saturation. To operate BJT in saturation. This will be the third step. Find minimum IB required to operate BJT in saturation. This minimum IB, it is nothing but IB at the onset of saturation. Little earlier I have told how much is IB at the onset of saturation. That itself will be called minimum IB required to operate BJT in saturation. You can call it as IB minimum. It will be equal to IC sat divided by beta. That base current at the onset of saturation, that itself will be called IB minimum. So in the exam they can ask question in this way also. Calculate minimum base current required to operate BJT in saturation. It is nothing but base current at the onset of saturation. So this is our third step. Okay, calculate this IB minimum. Then step number 4, fourth step. In fourth step, we compare IB and IB minimum. Compare IB and IB minimum. You have to perform comparison of IB and IB minimum. Whatever IB we got in step 2, that we should compare with IB minimum. Okay, whatever IB we calculate in this second step, this IB we should compare with IB minimum. If IB greater than IB minimum, that means BJT is in saturation. IB greater than or equal to IB minimum implies BJT is in saturation. And if IB less than IB minimum, if base current is less than IB minimum, then we say BJT is in active region. BJT is in active region. I hope everybody followed this procedure. It is based on whatever we have discussed in yesterday's class. This entire procedure, it is based on what we have learnt in yesterday's class. These are 4 simple steps. Okay, initially assume BJT in saturation, then find IB/IC, calculate IB minimum, and then compare IB and IB minimum. If IB greater than or equal to IB minimum, we will say BJT is in saturation. If IB less than IB minimum, then we say BJT is in active region. So everyone copy this procedure and try to remember it. This is an important topic, beta. Questions have come in the GATE paper as well as ESC paper based on this particular concept. Shruti, whatever IC we calculate in step 2 is nothing but IC sat. Okay, whatever IC we get in step 2, that will be nothing but IC sat only, क्योंकि हमने BJT को saturation में assume किया है. Yes or no? हमने यहाँ पर assume किया है कि BJT is in saturation, तो हम यहाँ पर जो भी IC find करेंगे, it is nothing but IC sat. Okay, we have assumed BJT in saturation, so whatever IC we calculate here, it will be nothing but IC sat only. Okay, that IC sat you divide with beta, you will get IB minimum, and then compare IB with IB minimum. Okay, IB more than IB minimum, BJT will be in saturation. IB less than IB minimum, BJT will be in active region. It's a very simple procedure which you all should remember. And by using this procedure, we will solve some questions. Let us take up a few questions here. You can note down this question, beta. Everybody write down this question. In circuit shown, BJT has beta equal to 100, VC is at 0.2 volt and VB is at 0.8 volt. Okay, find operating region. Find operating region of BJT, and you can take down this circuit also. In this circuit, we will try to find what is operating region of the BJT. So everyone copy this question first. Harshvardhan is asking, okay, what about cutoff? That I will tell you little later, beta. Whether BJT is in cutoff or not, we will discuss that little later. Bidisha Misra, beta, calculation of IB/IC, it will be different in different circuits. So once we solve questions, it will become clear to you. I will be solving here some important model of questions, so that will give you a clear idea how to calculate, IBIC. So let us solve this question. I will be using those, four steps. Whatever 4 steps I have told, I will apply those steps only. Step number 1, we assume BJT in saturation. Okay, this is our first step. Then step 2, we will find out IB and IC. I will indicate here, this is IB, base current, and here you can show collector current IC. Fine. Then you can indicate this as VCE, and this will be VBE. Fine. I have indicated IB, IC, then VBE and VCE. Then I will calculate first IB. In this circuit, emitter is directly grounded. Okay, in this particular circuit, emitter node is directly grounded. So we can say voltage between base and ground will be VBE. Therefore, when I calculate IB, that IB will be 5 minus VBE divided by 50. Okay, 5 volt minus VBE divided by 50. IB is equal to 5 minus VBE divided by 50K. We are taking a resistor in kilo ohm, 50 kilo ohm. 5 minus VBE divided by 50. You can put now VBE equal to VBE sat. VBE sat given in the question. तो ये चीज आप यहाँ पर substitute करिए. Put VBE sat as 0.8. It will become 5 minus 0.8 divided by 50. And calculate this IB. You will be getting it as some 0.084 milliampere. Okay, we have taken a resistor in kilo ohm, so current will be in milliampere. In this transistor circuits, a resistor will be mostly in kilo ohm, so current that we calculate will be in milliampere. Take resistor in kilo ohm and current will be in milliampere. So this was calculation of IB. Then we will also calculate IC. IC, or you can call it IC sat. What will be IC here? If you look at 3K resistor, voltage from here to ground is 10 volt, and voltage between this node and ground will be VCE. Okay, just look at this 3K resistor. Voltage from this node to ground is 10 volt, and voltage from this node to ground is VCE. So when I calculate IC, it will be 10 minus VCE divided by 3K. Fine. 10 volt minus VCE divided by 3K. 10 minus VCE divided by 3K. And you can put VCE as VCE sat. 10 minus 0.2 divided by 3K. 9.8 divided by 3. I'm getting a value 3.26. 3.26 milliampere. 3.26 milliampere. And you can call it IC sat also. Okay, you call it IC, or you can call it IC sat. This is step number 2, calculation of IB and IC. Now let us move to third step. What is third step? We should find out IB minimum. IB minimum is equal to IC sat divided by beta. Okay, IC sat is 3.26 divided by beta. Beta is 100. So this will be equal to 0.0326 milliampere. This is your IB minimum, 0.0326 milliampere. Then our step number 4. What is step number 4? Compare this IB and IB minimum. You have to compare IB with IB minimum. And what we notice here is IB is greater than IB minimum. This value 0.084, it is greater than 0.0326. So our conclusion is IB more than IB minimum. Let me write that point here. Step number 4. IB is greater than IB minimum. So we can say BJT is in saturation. BJT is in saturation. So for this question, operating region of the BJT is saturation region. It's a very simple procedure. Step 1 is only assumption. You have to do calculations in step 2 and step 3. And step 4 is only comparison. Okay. I hope everybody followed this procedure. In this particular question, BJT is in saturation. Rishta Kumari, yes beta, we can find this IBIC through KVL also. I have got here answers from so many of you. Yes beta, saturation region is the correct answer. All of you have given the correct answer. Saturation region. So please keep this procedure in the mind. It was a very simple circuit. Emitter is directly grounded here. So we are able to calculate IB and IC directly. 5 minus VB divided by 50, that is base current. 10 minus VC divided by 3K, that is collector current. We have got IB IC values directly because emitter is grounded here. Then we will take up the next question. I hope everybody has copied this part. We'll move to the next question. Beta equal to 100. VC is at 0.2 volt and VB is at 0.8 volt, and question is the same. Find operating region. Find operating region. Okay, this circuit is almost similar to the previous circuit, but I have now connected one extra resistor here between emitter and ground. Okay, this circuit is similar to the previous one, but we have now one additional resistor of 2K. So copy this question and try to solve it. We will apply the same 4 steps. So let's start solving it. Step 1, that is only assumption. Assume BJT in saturation. Then we have to calculate IB/IC. Let me show these currents. This is IB. Here you can show IC. This is VBE. Voltage between collector and emitter, it is VCE. And we will also show here current in the 2K resistor. Current in 2K resistor, it will be emitter current. And emitter current is always IB plus IC. Okay. Current in this 2K resistor, 2 kilo ohm resistor, it will be emitter current, and that emitter current is equal to IB plus IC. Now we cannot find IB directly here. You cannot calculate IB directly because there is a resistor 2 kilo ohm between emitter and ground. If emitter was directly grounded, I can find IB directly, but here we have a resistor of 2 kilo ohm between emitter and ground. Therefore we cannot calculate IB directly. So what we do here is we will apply KVL in 2 loops. First I will apply KVL in this loop. पहले हम इस लूप में KVL अप्लाई करेंगे बेटा, इसको हम कह देंगे loop 1. And then we will apply KVL in this loop also. This will be loop 2. Okay, first apply KVL in this loop. Ground to ground is a loop, so let us apply KVL in loop 1. KVL in loop 1, we get -5 plus 50 IB plus VBE plus 2 into IB plus IC is equal to 0. Okay, we have applied KVL here. -5 plus 50 IB plus VB plus 2 into IB plus IC is equal to 0. Then you rearrange it. 50 IB plus 2 IB, it will become 52 IB plus 2 IC is equal to 5 minus VB. 5 minus VB. You can substitute VB 0.8, VB equal to VB sat. So put VB as 0.8, it will become 4.2. This you can call as equation number 1. There are 2 unknowns here, so this you name as equation number 1. 52 IB plus 2 IC is equal to 4.2. This is our equation 1. And also remember, we have taken resistors in kilo ohm. So ultimately current will be in milliampere. Okay, that 50 is actually 50 kilo ohm, 50,000 ohm, but no need to write here 50,000. You can simply put 50. Later current will be in milliampere. Now there are 2 unknowns, IB, IC. So we have to make one more equation to form one more equation we will apply KVL in second loop. ठीक है, अब आप इस लूप में KVL अप्लाई करिए बेटा, KVL in loop 2. KVL in loop 2. That ground to ground is a loop. Fine. So apply KVL here. We get minus 10 plus 3IC plus VCE plus 2 into IB plus IC is equal to 0. Okay, I have applied KVL here. Minus 10 plus 3IC plus VCE plus 2 into IB plus IC is equal to 0. Then you rearrange this equation. It will become 2IB plus 5IC is equal to 10 minus VCE. Okay, 2IB plus 5IC, 3IC plus 2IC, it will be 5IC is equal to 10 minus VCE. And you can substitute here VCE equal to VCE sat 0.2 volt. 10 minus 0.2, it will become 9.8. This is our equation number 2. Now you should solve equation 1 and 2. There are two independent equations. By using KVL in loop 1, we got equation 1. By using KVL in loop 2, we got equation number 2. Now solve equations 1 and 2 and tell me how much is IB and IC. I am waiting for your answer beta. Dear students, please solve equations 1 and 2 and tell me how much is IB and IC. Solve equation 1 and 2. By solving these equations, tell me how much is IB and IC. I am waiting for your answers. I have got here answer from Ashutosh Pandey. Yes, beta Ashutosh, IB is equal to, first I will write IC. IC is 1.96 milliampere and IB it is 5.46 into 10 power minus 3 milliampere. Okay, you will be getting these values when you solve equation 1 and 2. Collector current 1.96 milliampere and IB 5.46 into 10 power minus 3 milliampere. I hope everybody getting the same answers. Yes, but I have got answers from Rashmika, then Khushi, Ayushi and Shashwat. Yes, beta, Aarti, Shruti, perfect. These are the values of collector current and base current. We have taken resistors in kilo ohm, that is why these values are in milliampere. That base current you can write as 5.46 microampere also, it is up to you. I have written it in this way. So this is our step number 2, calculation of IB and IC. Okay, because of this 2K resistor, we have to use KVL approach. Yes or no? Because there is a 2K resistor here, we have applied KVL in loop 1 and loop 2. If that 2K resistor is not there, if emitter directly grounded, then I can calculate IB/IC directly. Then move to step number 3. What is third step? Third step is find IB minimum. IB minimum, it is IC sat divided by beta. IC sat is 1.96 and beta is 100. It will be like 19.6 into 10 power minus 3 milliampere. Okay, 1.96 divided by 100, it will become 19.6 into 10 power minus 3 milliampere. Now we should compare IB and IB minimum, and you can easily say IB is less than IB minimum. Step number 4, IB is less than IB minimum. Now because IB less than IB minimum, our answer is BJT is in active region. BJT is in active region. IB is less than IB minimum here, therefore transistor is in active region. So for this question, correct answer is active region. So these two questions should give you the idea how to calculate IB, IC, right? In the previous problem, that emitter was directly grounded. In the first question, emitter was directly grounded, so we calculated IB, IC directly. 5 minus VB by 50, 10 minus VC by 3K. If emitter directly grounded, calculations become very easy. But if there is a resistor between emitter and ground, then we should follow this type of approach. Okay, when there is a resistor between emitter and ground, then you should find IB/IC with the help of KVL. Apply KVL in loop 1, apply KVL in loop 2, and then solve those two equations. You will get IB/IC. Some of you are asking this doubt, how to calculate IB/IC. I hope it is understood by everyone. Okay. Now in this question, we have got answer active region. Okay, transistor is not in saturation here, it is rather in active region. Okay, then you take next question. I hope everybody has copied it. We will solve the next question. The next question is a continuation of this problem only. Find IC and VCE in above problem. Find IC and VCE in above problem. Whatever problem we have solved just now. Okay, in that we will now find out what will be correct IC and VCE. Now please remember, whatever IC we calculated here, it was under the assumption that BJT is in saturation, but that assumption is proved to be wrong here. BJT is rather in active region. I hope everybody able to understand this point. हमने अभी जो क्वेश्चन सॉल्व किया है, यहां पर हमने इनिशियली अस्यूम किया था कि बीजेटी इज इन सैचुरेशन, फिर हमने आईसी को फाइन किया, बट आगे हमें पता चला कि बीजेटी इज नॉट इन सैचुरेशन, इट इज रैदर इन एक्टिव रीजन. तो ये जो आईसी हमने फाइन किया था ये एक्चुअली इनकरेक्ट होगा. दिस आईसी विल बी इनकरेक्ट, okay, because in this circuit BJT is not in saturation, it is rather in active region. So in our next problem we will calculate IC by considering BJT in active region. अब हम IC को दोबारा से फाइन करेंगे by considering transistor in active region. This is an extra question which I have given so that you get a complete idea. Okay, so let us solve it in this way. Recalculate IC by considering BJT in active region. By considering BJT in active region, सेम सर्किट को हम दोबारा से एनालाइज करेंगे by considering transistor in active region. Now when transistor is in active region we have to remember two things. This everybody note down this point. If BJT is in active region, then number one, you can apply this relation IC equal to beta IB. When BJT is in active region, we can use this relation IC approximately equal to beta IB. And we can also take IE, that IE, it is actually IB plus IC. Now you substitute IC as beta into IB. Here you put IC as beta into IB. So it will become 1 plus beta into IB. 1 plus beta into IB. Is that okay? Whenever transistor is in active region, we can use IC equal to beta IB and IE equal to 1 plus beta into IB. हमने IC की प्लेस में लिखा है beta IB. Just put IC equal to beta IB. Take IB common. It will become 1 plus beta into IB. Then number 2, whenever BJT is in active region, we should take VB equal to VB active. When a transistor is in active region, we should take VB equal to VB active. There is another value for VB, we call it VB active. Now this VB active, it is 0.7 volt for silicon transistor and 0.2 volt for germanium transistor, and these values I have written for NPN. If it is a PNP transistor, it will be minus 0.7 and minus 0.2. This is called VB active. VB when BJT is in active region. So these two properties we should apply when transistor is in active region. You can copy this point. These are all important things. If you remember these things, you will easily analyze any given BJT circuit. So same circuit we will analyze once again now by considering transistor in active region. मैं सर्किट को यहां दोबारा से ड्रॉ कर देता हूं. This is 10 volt, 5 volt. This resistor is 50k. This one is 3k and 2k. You can indicate here current IB. This is IC. And you can show current in this resistor, that will be IE. Now this IE I can take as 1 plus beta into IB. Okay, हम I को लिख देंगे 1 plus beta into IB, 1 plus beta IB. That beta is 100, so it will become 101 IB, 101 IB. Okay, because transistor is in active region, we can apply this relation IE equal to 1 plus beta into IB. That beta is 100, so emitter current will be how much? 101 IB. Then this you can indicate here VBE. This voltage is VCE. And now first apply KVL here in this loop 1. Okay, use KVL in loop 1. KVL in loop 1. We get minus 5 plus 50 IB plus VBE plus 2 into 101 IB is equal to 0. Okay, I have just applied KVL in this loop 1. Minus 5 plus 50 IB plus VBE plus 2 into 101 IB is equal to 0. अब आप इसको सॉल्व करिए बेटा and find out IB. Everyone solve this and find out IB. From here I can write IB equal to 5 minus VBE divided by 252. You can put VB as VB active 0.7 volt. So 5 minus 0.7 divided by 252. You will be getting it approximately 0.017 milliampere. This is base current. Base current is 0.017 milliampere. Now once we know base current, we can calculate collector current as well as emitter current. Collector current approximately equal to beta IB. You can substitute beta 100 and IB 0.017. So it will be like 100 into 0.017. It will be 1.7 milliampere. 1.7 milliampere. You can calculate emitter current also. Emitter current is 101 IB, or you can say IB plus IC. Emitter current can be found in two ways: IB plus IC or 101 into IB. 101 into IB. 1 plus beta into IB. If you calculate this, it will be 1.717 milliampere. So these are the BJT currents in the given circuit. We have obtained all three currents: IB, IC as well as IE. And we should also calculate here VCE. Question is to find VCE also. Okay, find IC and VCE in the above problem. So let us now calculate VCE. To find VCE, we will apply KVL in the second loop. We will now apply KVL here. This is our loop 2. Okay, use KVL in the second loop. उसको मैं यहां पे लिख देता हूं, KVL in loop 2. We get -10 plus 3IC plus VCE plus 2 into emitter current is equal to 0. Okay, KVL applied here, -10 plus 3IC plus VCE plus 2 into emitter current is equal to 0. This you rearrange. VCE is equal to 10 minus 3IC minus 2 into I. Okay, or VCE is equal to 10 minus 3 into IC. IC how much? 1.7 minus 2 into emitter current 1.717. And please remember, we have taken resistor in kilo ohm and current in milliampere. So kilo into milli it will cancel. रेजिस्टर की वैल्यू हमने लिखी है इन किलो ओम एंड करंट को हमने सब्स्टिट्यूट किया है इन मिली एम्पियर. तो जब आप मल्टीप्लाई करेंगे किलो इंटू मिली इट विल कैंसल आउट. आई होप एवरीबडी अंडरस्टूड दिस पॉइंट. वी हैव टेकन रेजिस्टर इन किलो ओम एंड करंट इन मिली एम्पियर. सो व्हेन यू मल्टीप्लाई किलो इंटू मिली इट विल कैंसल आउट. 3 kilo into 1.7 milli, kilo into milli it will cancel. And same thing here, 2 kilo into 1.717 milli. So this is the advantage of taking a resistor in kilo ohm. In these transistor circuits, resistor values are always in kilo ohm. So it is better to take resistor in kilo ohm and current in milliampere. And ultimately, when you put the values, that kilo into milli it will cancel. So tell me how much VCE. Please tell me that value VCE how much. I have got here answer from okay 1.436. I have got answer from Bidisha. एक बार चेक कर लेते हैं बेटा. $1.466. This is the correct value. 1.466 volt. Ashutosh, beta Ashutosh, we cannot calculate IC from loop 2 because we don't know VCE. So first you calculate IB by using KVL in loop 1. You cannot solve this question by starting with loop 2. हमने लूप 2 में KVL पहले अप्लाई नहीं किया बिकॉज वी डोंट नो VCE. तो अगर आप IC को लूप 2 से फाइंड करने की कोशिश करेंगे देन इट विल नॉट गिव यू द करेक्ट आंसर बिकॉज वी डोंट नो VCE. So the correct approach is first apply KVL in loop 1, calculate IB, from that IB calculate IC, calculate emitter current, then apply KVL in the second loop. You will get VCE. Okay, now don't put VCE equal to VCE sat here. VCE equal to VCE sat will happen when transistor is in saturation. Here transistor is in active region, and when a transistor is in active region, VCE can have any value. For saturation, VCE will be always VCE sat, but for active region, VCE can take on any value. Like here we got VCE 1.466. In some other circuit VCE can be 5 volt. In some other circuit VCE will be 8 volt. When a transistor is in active region, VCE can take on any value. I hope the doubt is clear beta. Yes, beta, this is the second class of analog electronics. We started analog electronics yesterday, and today is the second class of analog electronics. I hope everybody has understood these things. If you have doubts, please ask now itself. These are, good questions. This will give you a clarity how to calculate current and voltage in a given BJT circuit. Bidisha, all right, beta. Little error, it is okay. We do so many approximations in the calculation, so small variation can be there in the answer, that is acceptable. Then you can have a look at workbook. Please look at second chapter of the workbook. Everyone look at second chapter of analog workbook. In that second chapter, look at question number 2. Second chapter, question number 2. Everybody look at analog workbook, second chapter, question number 2. It is the same question which we have done just now, right? In second chapter, question number 2 is same as this only. So you can tick the answer. Tell me which option is correct. This is question number 2 in the second chapter. The correct answer will be option C. You can tick answer as option C. Transistor is in active region and VC 1.4 volt, approximately 1.4. Yes, beta, C option. Bidisha, Gayatri and Rishta. Option C is correct. Then look at question number 1. Please look at question number 1. Try to solve question number 1. A silicon transistor with VB at 0.8 volt, beta 100, VC at 0.2 volt is used in the circuit shown below. What is the minimum value of RC for which transistor is in saturation? Okay, we have to calculate minimum value of RC for which transistor is in saturation. Yes, but Chandrakant, we should take emitter current also in milliampere. When you substitute collector current, emitter current, you take them in milliampere. Milli into kilo, it will cancel. So look at question number 1. The circuit given is like this. This is 5 volt. Then here is 200k and RC. This is 10 volt. Beta is given 100. VB is at 0.8 and VC is at 0.2 volt, and we have to calculate the value of RC. Okay, find minimum value of RC for which transistor is in saturation. Minimum value of RC for which transistor is in saturation. Now to solve this question, we will first of all calculate IB. पहले हम IB फाइंड करेंगे बेटा. Emitter is directly grounded, so we can calculate IB directly. 5 minus VB divided by 200. IB is equal to 5 minus VBE divided by 200k. Then put VB as VB is at 5 minus 0.8, it will be like 4.2 divided by 200. You will get it as 0.021 milliampere. Base current is 0.021 milliampere. Then you calculate IC also, collector current. Collector current will be 10 minus VC divided by RC. IC is equal to 10 minus VCE divided by RC. VC, you can substitute VCE sat. Okay, we are finding here RC such that transistor is in saturation. Please read the question carefully. We have to calculate here RC such that transistor is in saturation. So put VC equal to VCE sat 0.2. It will become 9.8 divided by RC. Then we will obtain IB minimum. It is IC sat divided by beta. It will become 9.8 divided by 100 RC. Okay, beta is given as 100. So 9.8 divided by 100 RC. Now you can apply this condition कि transistor operates in saturation if IB greater than IB minimum. अब हम ये कंडीशन अप्लाई कर लेंगे. BJT operates in saturation. BJT operates in saturation if IB greater than or equal to IB minimum. Okay, we have to calculate here RC such that transistor is in saturation. When transistor is in saturation, IB should be greater than IB minimum. तो यहाँ पर आप पुट करिए IB 0.021 more than or equal to 9.8 divided by 100 RC. From here you calculate RC. You will get RC more than or equal to 4.666 kilo ohms. Okay, calculate RC, you will get it this much. That means RC should be 4667 ohms. If you look at the options, the correct option will be option B. Okay, correct answer will be 4667 ohms. Shreyas, beta, we will try to solve, maximum number of questions in the class itself. Yes, beta, option B is correct. All of you have given the correct answer, option B. Bhavana, beta, IC equal to beta IB, it is for active region only. So we have obtained here first IB, फिर हमने IC को फाइंड किया, then we have written IB minimum. Okay, IB minimum means base current at the onset of saturation, or minimum base current required to operate transistor in saturation, that we have calculated 9.8 by 100 RC. Then we have applied the condition IB greater than IB minimum. Transistor has to be in saturation here, so we have applied the condition IB greater than IB minimum, and from that condition we have got RC. So this is your correct answer, B option. You can look at question number 3 also. Please have a look at question number 3. It is from 2014 GATE paper. Everybody look at question number 3. क्वेश्चन नंबर 3 बेटा, इसको सॉल्व करिए आप. Here beta is given as 50, beta equal to 50. VC sat given 0.2 and VB given 0.7, VB equal to 0.7, and we have to tell which of the following statements is correct. Okay, those options, they are about the value of RC only. Which of the following statements is correct? Now what we will do is we will calculate first of all IB. पहले हम IB फाइंड कर लेते हैं बेटा. Let us calculate IB. IB is equal to 5 minus VBE divided by 50. Now in the question VB is given 0.7. In the GATE paper you should use only the given data. In GATE examination we don't assume data, we should use only the data which is given in the question. In the question VB given 0.7, so use 0.7. Okay, if they give you VB is at 0.8, then you can use that 0.8, but here they did not give VB sat, they have simply given VB 0.7, so use given VB. In GATE examination we should never assume data. Whatever data is given in the question, use that and solve. So put VB 0.7, 5 minus 0.7 divided by 50. You will be getting here IB 0.086 milliampere. Okay, that 50 is in kilo ohm, 50k, so current will be in milliampere. Then we will calculate IC sat. अब हम IC sat फाइंड करेंगे बेटा. IC sat is equal to 10 minus VCE divided by RC. Okay, you can substitute VCE sat, that VCE sat it is given in the question 0.2. तो अब आप यहाँ पर लिखिए VCE 0.2, 10 minus 0.2 it will become 9.8 divided by RC. So this is IC sat. Then I will obtain IB minimum. IB minimum is equal to IC sat divided by beta. It will be 9.8 divided by 50 RC. Beta is given as 50, so 50 RC. Then we can use condition, okay, transistor will be in saturation if IB greater than IB minimum. Okay, from that condition we will try to calculate RC. BJT operates in saturation if IB greater than or equal to IB minimum. ठीक है, you substitute here IB 0.086 more than or equal to 9.8 divided by 50 RC. From here calculate RC. Just find out RC. $2.28 kilo ohms. I'm getting RC greater than 2.28 kilo ohms. I think this will help you in deciding which option is correct. If RC greater than 2.28 kilo ohm, transistor will be in saturation. Now you look at the options and tell me which option is correct. Yes beta, Abhinav, Rishta, then Hema. Yes, for third question correct answer should be option B. Option A will be wrong. For RC equal to 1K, transistor will be in active region. Okay, for RC greater than 2.28, transistor is in saturation. If RC less than 2.28, transistor will be in active region. Okay, so option A will be wrong. Option B is correct. For RC 3K, BJT operates in saturation. So for this question, correct answer is option B. C and D, they will be of course false. For RC equal to 20K, BJT will be in saturation only. So C and D, they are incorrect. Option B is correct. For RC equal to 3K, transistor will be in saturation. Yes, I have got answers from Hushi, then Milu John, then Shruti and Anu John. Option B is correct. This was a 2 marks question in 2014 GATE paper. It was asked for 2 marks. Quite easy to solve. Okay. We have obtained IB. Then we have obtained IC sat. We calculated IB minimum. Then we applied this condition. BJT operates in saturation if IB greater than IB minimum. And from this condition, we get RC. And once we know RC, we can easily tell which option is correct. Then you can look at one more question which appeared in 2017 gate paper. Question number 27. Everybody look at question number 27. Nishita is asking, okay, what will happen if there are more options with RC greater than 2.28? But such questions can come as MSQ, multiple select question, where more than one option can be correct. But in MCQ, they will prepare options such that only one is correct. Okay. Shruti, yes beta. In case of BJT, linear region refers to active region. In case of BJT, active region can be sometimes called linear region. Now please try to solve question number 27. I want everyone to attempt question number 27. This question appeared in 2017 gate paper for 2 marks. Input is given here. Input is like a pulse. Input is like a pulse signal. This type of input is given, and question says, for the input shown, transistor switches between cutoff and saturation. Okay, VC is at 0.2 volt, VB 0.7 volt. You have to calculate minimum value of common base current gain alpha. You have to obtain here minimum value of alpha. That alpha is called common base current gain. That you have to calculate here. This type of pulse input is applied here. Okay, input is like a pulse, and it is quite obvious when input is 0, transistor should be in cutoff, and when input equal to 2 volt, transistor should be in saturation. Okay, when input is 0, transistor should be in cutoff, and when input equal to 2 volt, transistor should be in saturation. It is told in the question, for input shown, transistor switches between cutoff and saturation. That hint is given in the question. तो क्वेश्चन से ही हमें ये चीज समझ में आएगी कि जब इनपुट 0 होगा, ट्रांजिस्टर कट ऑफ में ऑपरेट करेगा, और जब इनपुट इज 2 वोल्ट, ट्रांजिस्टर विल गो इनटू सैचुरेशन. Let me just write this point here. Vi 0, then BJT in cutoff, and when Vi 2 volt, transistor should be in saturation, BJT in saturation. We will first of all calculate IB. ठीक है, पहले हम IB फाइंड कर लेते हैं. Let us obtain IB. I will calculate here IB. IB is equal to that VI minus VBE divided by 12K. VI minus VBE divided by 12K. Now here we should actually take VBE as VBE sat, but in the question VBE sat not given, so we should take only given VBE. This is what I am telling you. In GATE paper we never assume data, so whatever data is provided in the question, only that data we should apply. Okay, ideally speaking VBE should be VBE sat here, but VBE sat not given, so we should take given VBE 0.7. okay, so you put VBE 0.7, it will be like 2 minus 0.7 divided by 12. Calculate IB. It is 0.1083. IB is equal to 0.1083 milliampere. Okay, resistor is in kilo ohm, so current will be in milliampere. 0.1083 milliampere. Then we will calculate here IC. You can call it IC sat also. IC sat. It will be 5 minus VCE divided by 4.8. Put VCE as 0.2. VCE sat. So it will be 1 milliampere. Okay, resistor is in kilo ohm, so current will be in milliampere. This is your IC sat. We have taken VCE equal to VCE sat. Then we will obtain IB minimum. It will be IC sat divided by beta. That beta is unknown, so keep beta as it is. 1 by beta milliampere. 1 divided by beta milliampere. Now you apply the condition. BJT operates in saturation. BJT operates in saturation if IB greater than or equal to IB minimum. Okay, now here IB is 0.1083, more than or equal to 1 upon beta. From here you will obtain beta. Beta more than or equal to 9.23 some 36 or 9.234, let us say. Beta greater than 9.234. Now beta will be called common emitter current gain. This value beta, it will be called common emitter current gain. But the question is common base current gain. You have to calculate alpha. Yesterday I have given you relation between alpha and beta. We know beta, so we can calculate alpha. Alpha is equal to beta upon 1 plus beta. Okay, if you know beta, you can calculate alpha. So you put here this beta, it will be like 9.234 divided by 1 plus 9.234. I will be getting here alpha equal to 0.902. This is the answer. This is the minimum alpha in the given question, 0.902. This question appeared in 2017 GATE paper for 2 marks. and we can easily solve it by using this method number 1. Okay, alpha equal to 0.902. Yes beta, I have got answer for this question from like many of you. Perfect. Veena, then Khushi, Rishta, Shashwat, Abhinav, Bidisha, Agaliya Shiva, Hema, Bhavna, Bidisha, Veena. Yes beta, perfect. 0.902. That is the answer. So remember, beta will be called common emitter current gain and alpha will be called common base current gain. Abhinav, beta, we know condition in terms of IB. IB greater than IB minimum. So it is better if you find IB and IB minimum and then apply the condition. Okay. We know the condition of saturation in terms of IB. IB greater than IB minimum, transistor is in saturation. So you should solve question in terms of IB and IB minimum. You can take alpha as IC upon IE also, but we have learnt the approach in terms of IB and IB minimum, so better to go with that condition. Now all these questions, they had a NPN transistor. Whatever problems we have done so far, in all these questions there was a NPN transistor. I will now take up one question with the PNP transistor also, so that you get a complete idea. Okay, we will try one question with PNP transistor also. You can copy this question, and this question came in mains paper. This particular question which we solve now, it has come in one of the previous mains ESC papers. Okay, so please take down this question. Beta equal to 100 VCE sat minus 0.2 volt, VB sat minus 0.8 volt. Question is find operating region and V0. Okay, some voltage V0. This question appeared in one of the previous mains ESC paper. It has a PNP transistor. That is why these voltages are given as negative, minus 0.2 and minus 0.8. You have to find operating region and output voltage V0. Copy this question, then we will try to solve it. Let us try this question. It has a PNP transistor here, and these voltages, they are like minus 3, minus 10. Now when I show here minus 3, it means between this point and ground you have a battery of 3 volt whose negative terminal is connected to this node. Okay, if I show here minus 3, it means between this node and ground we have a battery of 3 volt whose negative terminal is connected to this node. Okay, the actual connection it will be in this way. हम इसको ऐसे दिखा देंगे. It will make easy when we apply KVL. Minus 3 means it will be in this way. Okay, negative terminal connected to this node. And similarly here we have minus 10. That means between this node and ground we have a battery of 10 volt whose negative terminal connected to this node. So actual connection will be like this, 10 volt. Okay, minus 10 implies this negative terminal is connected to this node. And similarly here minus 3 means negative terminal connected to this node. If it is plus 3, it means positive terminal connected to that node. I hope everybody is getting clarity. So let us solve this question. We have to find operating region, right? तो पहले हम assume कर लेते हैं. Step 1, assume BJT in saturation. Assume BJT in saturation. Then we have to calculate IB and IC, right? It is a PNP transistor. For PNP transistor, current directions are opposite. NPN and PNP, current directions will be opposite. So let me show here currents first of all. This will be IB. This is IC. And here we can indicate IE. And that IE, it will be equal to IB plus IC. So keep this in mind. For PNP transistor, current directions are opposite. IE flows into the transistor and IB, IC, they flow out. Okay, remember this difference. For PNP transistor, IB, IC, they flow out. Okay, and IE flows inward. Then you can show here VBE, and you can indicate here VCE, VBE and VCE. Now apply KVL. We will first apply KVL here. You can call it loop 1. And we have to apply KVL in second loop also. I will show that here. loop 2. Okay, first we will apply KVL in loop 1. This is our step number 2. KVL in loop 1. I'm traveling in this way. Okay, so it will be 0.5 into IB plus IC minus VBE plus 7IB minus 3 is equal to 0. 0.5 into IB plus IC, okay, minus VBE plus 7IB minus 3 is equal to 0. I have applied KVL from ground to ground. We get 0.5 into IB plus IC minus VBE plus 7IB minus 3 is equal to 0. This you rearrange, it will become 7.5 IB plus 0.5 IC is equal to 3 plus VBE. 3 plus VBE. Now we should substitute VBE. In the question, VBE sat is given minus 0.8. So put minus 0.8. This VBE, it will be how much? Minus 0.8. So it will become 2.2. This we can call equation number 1. Okay, we have written VBE how much? Minus 0.8. So it will become 3 minus 0.8, 2.2. So this is our equation number 1. There are two unknowns, IB, IC. So we have to apply KVL in the second loop also. By using KVL in the second loop, we will get one more equation. Let us apply KVL in loop 2. KVL in loop 2. We get 0.5 into IB plus IC minus VCE plus 3IC minus 10 is equal to 0. Okay, I have applied KVL here. 0.5 into IB plus IC minus VCE plus 3IC minus 10 is equal to 0. This you rearrange, it will become 0.5 into IB plus 3.5 into IC is equal to 10 plus VCE. You can put VCE how much? Minus 0.2. It is a PNP transistor. PNP transistor, that VCE will be negative, minus 0.2. So 10 minus 0.2, it will become 9.8. This is our second equation. Now solve equation 1 and 2 and tell me how much is IB and IC. Please solve equation 1 and 2 and tell me how much is IB and IC. Solve equation 1 and 2 and tell me what are the values of IC and IB. Okay, I have got answer from Bidisha. IB 0.107 and IC 2.78. Yes beta, Ayushi and then Veena perfect. 0.107 is IB and 2.78 is IC. 2.784 milliampere and 0.107 milliampere. Yes beta, Sneha, Ashutosh, Rashmika, Aarti and then Ayushi. 0.107 and 2.784. Yes Shruti, these are the values of IC and IB. Okay, फिर हम आगे फाइंड करेंगे IB minimum. Let us calculate now IB minimum. That will be our third step. IB minimum. It is IC sat divided by beta. Okay, that IC sat, it is 2.784 divided by beta. Beta is 100, so it will be 0.02784 milliampere. Okay, 2.784 divided by 100. Then compare IB with IB minimum. IB is greater than IB minimum. Okay, our fourth step, IB greater than IB minimum. Therefore, transistor is in saturation. BJT is in saturation. So this was a question with PNP transistor. I just wanted to give you the idea that how we analyze a circuit having PNP transistor. For PNP transistor, current directions are opposite and VB, VC, they will be negative. So these two differences you should remember. Okay, for PNP transistor, current directions are opposite and VB, VC are negative. I hope it is clear. So the correct answer is saturation. This question appeared in mains ESC paper. And we should also find out here V0. Question is also about calculate V0. We have to obtain this V0. So let us find that V0 also. You can calculate V0 by traveling from this node to ground. V0 is nothing but voltage between collector and ground. Here V0 is nothing but voltage between collector and ground. So you travel from collector to ground. If you travel in the upward direction, V0 will be 3 into IC minus 10. V0 is equal to 3 into IC minus 10. Okay, I have traveled in the upward direction. 3 into IC minus 10. You substitute here IC. 3 into 2.784 minus 10. And just observe, resistor is in kilo ohm and current is in milliampere. Kilo into milli, it will cancel. So tell me how much is V0? Minus 1.64. I'm getting a value minus 1.64 volt. Minus 1.64. You can calculate V0 by traveling in the downward direction also. Okay, here I have calculated V0 by traveling in the upward direction. You can find V0 also by traveling in downward direction. If you are moving in the downward direction, then V0 will be in this way. or V naught is equal to VCE minus 0.5 into IB plus IC. If you are moving in the downward direction, then V naught will be VCE minus 0.5 into IB plus IC. It will be minus here because current is in the upward direction and we are moving down. Okay, you can calculate V naught in this way also. You put here VCE minus 0.2, put VCE minus 0.2, you know IB, IC, put all the values, you will get same answer, minus 1.64. You can cross check, you will be getting almost same answer. That V naught is voltage between collector and ground. You travel in the upward direction, you will get V naught in this way, or you travel in the downward direction, you will get V naught in this way, and both answers they will be same, minus 1.64. And if you take IC 2.78, it will be, I think, minus 1.66. That small error it can be there because we do some approximations here. Minus 1.66 minus 1.64, it is perfect. So this was our method number 1. Okay, we have tried all these questions by using method number 1. There is one more method to find operating region. I will discuss that second method also. Whatever questions we have done here, we have tried all of this using method number 1. This was our method number 1. हमने अब तक जो कुछ भी किया है बेटा, we have done it using this 4 steps. There is another method for finding operating region, so I will not discuss the other method, how to find operating region in another method. In exam you can use any method. I will teach both methods here. In exam you apply any method, you will get same answer. So please take method number 2. Method number 2. In method number 2, you write step number 1. Assume BJT in active region. Assume BJT in active region. Method number 1, we were assuming BJT in saturation. Method number 2, we assume BJT in active region. Active region. Then step 2. Calculate VCE. Calculate VCE, collector to emitter voltage. And please remember, when you are using this method 2, you are assuming transistor in active region here, so you can apply IC equal to beta IB, IE equal to 1 plus beta IB. Those relations become valid here. Okay, and calculate VCE. Step 3, compare VCE and VBE. You have to compare here VCE and VBE. VCE should be compared with VBE, and there are two possibilities: VCE greater than or equal to VBE. It means transistor is in active region, and VCE less than VBE, that means transistor is in saturation. Region, and this I have written with respect to NPN transistor. Okay, you can copy this procedure also. This is another method of finding operating region. You assume here transistor in active region and calculate VCE and then compare VCE and VBE. यहाँ पर आप VCE को VBE से कंपेयर करेंगे. अगर VCE ग्रेटर देन VBE होगा तब हम कहेंगे ट्रांजिस्टर इज इन एक्टिव रीजन, और अगर VCE लेस देन VBE होगा तब हम कहेंगे ट्रांजिस्टर इज इन सैचुरेशन. This I have written with respect to NPN transistor. Okay, if it is a PNP transistor, then we should calculate VEC. If it is a PNP transistor, we should find VEC and we should compare VEC with VEB. Is that clear? अगर आप चाहो तो उसको लिख लो अलग से एज ए नोट. For PNP BJT, compare VEC and VEB. VEC greater than VEB implies active region, and active region can be called linear region also. One of you was asking as a doubt, in BJT active region can also be called linear region. Sometimes they will use linear region terminology also. So please remember, in case of BJT, active region can also be called linear region, and VEC less than VEB implies saturation. Saturation region. That approach is the same. For NPN we consider VCE, VBE. For PNP we should consider VEC and VEB. For PNP, VCE, VBE are negative. For PNP transistor, VCE, VBE are negative. So to remove that minus sign, we should take VEC and VEB. I hope the point is understood. In case of PNP transistor, VCE, VBE are negative values. To remove that minus sign, we consider VEC and VEB. VEC, VEB, they will be positive. So comparison will become easy. So this is your method number 2. And sometimes when we solve this type of questions, we may get base current negative. When we solve a question like this, sometimes we may get base current negative. If you find IB negative, it implies transistor is in cutoff. Okay, one of you was asking this also as a doubt in the beginning. So please remember, when you apply this method 2, if you get IB negative, it means transistor is in cutoff. You can write that as a note. If IB is negative, that implies BJT is in cutoff region. When you apply this method 2, when you use method 2, if you get IB negative, base current negative, it means transistor is in cutoff. Please copy this method. Aditi, beta, I hope your doubt is clear. I have written the condition separately for PNP. That should clear your doubt. I have got one more doubt here. Milu John is asking, what is the logic behind VCE greater than VBE? We are actually comparing collector voltage and base voltage. Okay, this VCE greater than VBE, we are actually comparing collector and base voltage. You can think like this. If you look at NPN transistor, this is your NPN transistor. Okay, this is N, this is P, and this is N. NPN transistor, collector is N type, base P type, and emitter N type. When we compare VCE and VBE, we are actually comparing collector voltage with base voltage. Is it clear? VCE greater than VBE implies collector voltage more than base voltage. It should be understood in this way. VCE greater than VBE implies collector voltage is greater than base voltage. Okay, and remember, collector is N type and base P type. If N voltage greater than P voltage, it means that collector junction is in reverse bias. Okay, collector voltage more than base voltage, it implies N voltage is more than P voltage. If N voltage more than P voltage, it is nothing but reverse bias. Collector junction in reverse bias. Collector junction in reverse bias. And collector junction will be in reverse bias in active region. Yes or no? If collector junction in forward bias, that will become saturation. If collector junction in reverse bias, it will be active region. I hope the logic is understood. Okay, collector is N type here and base P type. So collector voltage more than base voltage means N voltage is more than P voltage. N voltage more than P voltage implies reverse biasing. Collector junction is in reverse bias. That means transistor is in active region. I hope the logic is clear. Then I have got it out from Sohini. K IB negative, that node is valid for method 1 or not. For method 1, if IB negative, then you have to carry out one more step. This note I have written for method number 2. If IB negative, then BJT is in cutoff. This note is for method number 2. In method number 1, if I get IB negative, then I have to perform one more step. If you want, you can write that also as a note. Let me go back to method number 1. But this was our method number 1. Okay. This was our method number 1. Sometimes in method number 1 also you may get IB negative. Sometimes in method number 1 also we may get IB negative. So along with method number 1 you can take one note. Along with method number 1 you take this note. If IB is negative, then if you are getting IB negative, then there are two possibilities here. Transistor can be in cutoff or transistor can be in active region also. Okay, this note is for method number 1. Okay, अगर आप कोई क्वेश्चन सॉल्व कर रहे हैं विथ मेथड 1, if you get IB negative, then it may imply two things. Transistor may be in cutoff, transistor may be in active region. So what you should do here is you should carry out one extra step. Okay, that extra step is, if IB is negative, then calculate VBE by assuming BJT as off. Okay, in case you get IB negative here, then you should assume BJT as off and calculate VBE. Then you compare VBE with VBE cut-in. Compare VBE and VBE cut-in. Okay, and there are two possibilities. VBE less than VBE cut-in implies transistor is in cutoff region. If you get VBE greater than VBE cut-in, that means transistor is in active region. Okay, so this note you can copy with method number 1. Do not get confused, beta. I am telling you everything with absolute clarity. This note you will apply for method number 1. So when you copy this, you copy it along with method number 1 so that there is no confusion. This is your method number 1. Along with the method number 1, you can copy this note. Sohini and Rishta, I hope beta your doubt is clear. So this note is for method number one. Okay, and method number two, you can directly say transistor is in cutoff. In method number two, if you get IB negative, you can directly say transistor is in cutoff. When you apply method 2, if you get IB negative, you can directly say transistor is in cutoff. In method number 1, if IB negative, we have to perform extra step. Calculate VB by assuming BJT as off, compare VB with VBE cut in, then you decide whether it is cutoff or active region. But in method number 2, I can directly tell transistor is in cutoff. And we will try our first question with method number 2. In the beginning we have done this question, right? Yep. This same problem I will now try with method number 2. Okay, if you want, you can copy this question once again. Same circuit I will try once again. आप इसको मेथड 2 से ट्राई करेंगे बेटा. जो भी क्वेश्चन हमने शुरुआत में किया था, वट एवर क्वेश्चन वी हैव डन इन द बिगिनिंग, सेम क्वेश्चन वी विल ट्राई विद मेथड नंबर 2. You will get same answer. So when I solve it with method 2, I'm going to assume BJT in active region, right? Assume BJT in active region. Fine. Active region. Then we will calculate IB. पहले हम IB फाइंड कर लेंगे. It will be 5 minus VBE divided by 50. We will calculate IB. 5 minus VB divided by 50. Then you put VB equal to 0.7. Okay, active region. So we should put VB active. VB active is how much? 0.7. So 5 minus 0.7 divided by 50. तो आप यहां से IB फाइंड कर लो बेटा. It will be 0.086 milliampere. Then calculate IC. Because we are assuming BJT in the active region, we can apply this relation IC equal to beta IB. Okay, we have assumed transistor in active region, so we can apply IC equal to beta IB. That beta is 100. तो आप multiply कर लो 100 into this much. 100 into 0.086. It will be 8.6 milliampere. Okay. Then calculate VCE. अब आप VCE फाइंड करिए. You can apply KVL like this. You apply KVL in this loop. We get minus 10 plus 3IC plus VCE is equal to 0. KVL. Minus 10 plus 3IC plus VCE is equal to 0. So I will be getting here VCE equal to 10 minus 3IC. Okay, it will be 10 minus 3 into 8.6. We have taken resistor in kilo ohm, current in milliampere. Kilo into milli it will cancel. Okay, resistor को हमने लिखा है in kilo ohm और करंट की वैल्यू हमने पुट की है इन मिली एम्पियर. किलो इंटू मिली इट विल कैंसिल. सो कैलकुलेट हियर VCE. VCE is equal to, just tell me how much VCE. I'm getting minus 15.8. Minus 15.8 volt. I have got VCE minus 15.8. Now that this clearly implies कि VCE is less than VBE. ठीक है, we are comparing VCE and VBE here. Vc less than Vb, so transistor is in saturation. It implies saturation. Saturation region. So you can try the question with any method, either method 1 or you can use method 2. In method 1, we were comparing IB and IB minimum and we got answer saturation. In method number 2, we compare Vc and Vb and we get same answer, saturation. VB cut-in I gave yesterday beta, Khushi Verma. VB cut-in 0.6 for silicon, 0.1 for germanium. That I told yesterday. Aditi and Khushi. VB cut-in I discussed yesterday. VB cut-in is 0.6 for silicon, 0.1 for germanium. Gayatri, yes beta, that note IB note is valid for both NP and PNP, but the only difference is for PNP you will compare VEB and VEB cut-in. You can try the next question also using method number 2. This question also you can solve using method number 2. Do it as a homework. The second question, please try this as a homework. Solve using method 2. Everybody perform this as a homework. Okay, that second question where we have a extra 2k resistor, try this question as a homework using method number 2. You will get same answer, active region. And Gayatri is asking a doubt about this note, this IB note. This is like with respect to NPN. If it is a PNP, you have to compare VEB and VEB cut-in. Okay, for PNP VB is negative, तो वहां पर आप VEB फाइंड करिए, उसको कंपेयर करिए विथ VEB cut-in. VEB and VEB cut-in. If it is a PNP transistor, instead of taking VB, you should take VEB. Compare VEB and VEB cut-in. Now that type of question will be very rare. Okay, mostly in gate paper they will give you circuit with NPN transistor. If it is a NPN transistor, you should compare VB and VB cut-in. PNP hoga, then compare VEB and VEB cut-in. VEB less than VEB cut-in, cut off. VEB greater than VEB cut-in, it will be active region. So everyone has understood these things. Okay, we will now solve question number 4. Let us try question number 4 from the workbook. It is from 2007 gate paper. Please look at question number 4. Everybody read question number 4 from the workbook. It appeared in 2007 gate paper. For the BJT circuit shown, assume that beta of the transistor is very large and VB 0.7, you have to tell what is mode of operation of the BJT. What is mode of operation of the BJT? Now tell me, what should we do here? Question number 4. Shashwat, beta, when you apply method 2, then for PNP transistor you compare VEC and VEB. Okay, you can compare magnitude also, but it will be better if you apply this approach. Okay, instead of VCE VB, you take VEC and VEB. Okay, you can compare magnitude also, mod VC greater than mod VB active region, mod VC less than mod VB, it will be saturation. You can do it in that way also, but the safe approach, okay, the more appropriate approach will be like this. You should compare VEC and VEB. So please tell me, what should we do in question number 4? In question number 4, beta is unknown, beta value unknown. Beta is unknown. Now when beta is unknown, method 1 cannot be applied. When beta is unknown, we cannot apply method number 1, because in method number 1 we have to find IB minimum. IB minimum is equal to IC sat divided by beta. If that beta is unknown, we cannot use method 1. So we should try this question only with method 2. Okay, beta is unknown, so method 1 cannot be used. So apply method 2. If beta is given, you can try question with any method. अगर हमें बीटा की वैल्यू पता होगी, then we can apply method 1 or method 2, anything. But if beta is unknown, then method 1 does not work. So we have to go for only method 2. तो अब हम इस क्वेश्चन को ट्राई करेंगे with method number 2. Okay, I will first draw the circuit here. Okay, this is the circuit given in this question number 4. तो पहले हम यहां पर अस्यूम करेंगे कि ट्रांजिस्टर इज इन एक्टिव रीजन. अस्यूम BJT in active region. Then you can show here this current IB, sorry, this is IC, and here you can show current IE, emitter current. This will be VBE. Okay, first we will apply KVL here. Let us apply KVL here. We get -2 plus VBE plus 1 into IE is equal to 0. I have just applied KVL here. Minus 2 plus VBE plus 1 into IE is equal to 0. So from here I will get IE is equal to 2 minus VBE. That VBE given as 0.7. So it will be 1.3 milliampere. Okay. I have calculated here emitter current 1.3 milliampere. VB it is provided in the question 0.7. तो हमने इस तरह से एमिटर करंट को फाइंड कर लिया. Now if beta is unknown, then we neglect IB and we take IC approximately equal to IE. This also you should remember. Whenever beta is unknown or when question says BJT has a large beta, in that case you neglect IB. When IB is neglected, then IE will be like approximately equal. Fine. So please remember this. Beta is very large implies neglect IB. And you can take IE approximately equal to IC. Everybody should remember this point. This type of questions have come in the GATE. Question will say in the circuit shown BJT has a very high beta. So in such questions you ignore IB, and when we ignore IB, then IE they will become approximately same. So this property I am going to apply. We have obtained here IE 1.3. We can take IC also as 1.3. IC approximately equal to IE 1.3 milliampere. Okay. Then we will calculate this VCE. We will now find out this VCE. Apply KVL here. We get minus 10 plus 10 IC, okay, plus VCE plus 1 into IE is equal to 0. I have applied KVL here. Minus 10 plus 10 IC plus VCE plus 1 into IE is equal to 0. Now IE, IC, they are like approximately equal here. So I will get VCE equal to 10 minus 11 IC. Okay. That IE, IC, we are approximating them. So it will become 10 minus 11 IC. Substitute here IC, 10 minus 11 into 1.3. And tell me how much is VCE. 10 minus 11 into 1.3. Minus 4.3. I'm getting a value minus 4.3 volt. And we can now say that VCE is less than VBE. VCE less than VBE. Therefore, BJT is in saturation. BJT is in saturation. So for this question number 4, correct answer is saturation. I think Bidisha, I hope it is clear beta. Transistor is in saturation here. So the correct answer should be option B. Yes, I have got answer from Bidisha, Abhinav, then Anujan, Bhavna, Gayatri. Yes, saturation region is the correct answer. Beta is unknown here, so method 1 cannot be used. Remember this. In method 1, we need beta because in method 1, we have to calculate IB minimum. IB minimum is equal to IC sat divided by beta. So when beta is unknown, we cannot apply method 1. In such case, you should apply only method 2. Apply method 2. Okay, this is the approach for method number 2. And because beta unknown here, we neglect IB and we take I approximately equal to IC. This is an important point. Please highlight this. इसको आप याद रखिए. Okay, put this in a box and highlight this important point so that next time you come across such a question, you can apply this approximation. Now in the same question, let us say this 10k resistor replaced by 5k. Then tell me what will be the answer. Everything same, only replace 10k with 5k. Let us say 10k resistor replaced by 5k. And now tell me what will be the region of operation. Please tell me through comment. 10k replaced by 5k. What will be region of operation? Okay, I have got here answers from Khushi, then Bidisha, Bhavna, and Abhinav. Active region. Yes, beta. Sai Kiran. Active region. Yes, we will now get VCE 2.2. If you replace 10k with 5k, you will get VCE 2.2. Okay, and that means active region. Your answer will be active region. Same circuit, we have just replaced 10k with 5k. Then apply same step, you will get VCE 2.2 volt. That means VCE greater than VB, so we can conclude transistor is in active region. So this was all about how to find the operating region. We will move now to the next topic. Okay, I hope everybody has understood this topic thoroughly. Keep in mind both method 1 and method 2. Okay, remember both methods. In exam you apply any method. Okay, if beta unknown, then use only method 2. If beta is given, you can use either method 1 or method 2. Let us move to the next topic. Our next topic will be load line, DC load line. You can make a heading DC load line. And one of you is asking about timing for tomorrow's class. Nishita is asking what is timing for tomorrow's class. But tomorrow we will have class from 1 to 9. Tomorrow class will be from 1 to 9. Tomorrow is Saturday, so we will have a longer session tomorrow between 1 to 9. Now make a heading DC load line. You can take couple of points about it. DC load line. You can take down this sentence. It is a straight line. It is a straight line plotted on IC versus VCE graph. It is a straight line plotted on IC versus VCE graph. Okay, it's a straight line plotted on IC versus VCE graph. And this DC load line, it will be used in graphical analysis, especially when we analyze power amplifiers. In the analysis of power amplifier, we use DC load line in graphical analysis. You can take this point also. It is used in graphical analysis. Graphical analysis of BJT circuits. Okay, so keep in mind these two sentences. DC load line means it is a straight line which we plot on IC versus VCE graph, and this DC load line, it will be used in graphical analysis. You can take one more point. Equation of DC load line is obtained. Equation of DC load line is obtained by applying KVL. By applying KVL in collector loop. Collector loop. If I give you a BJT circuit, and I ask you to draw its DC load line, then you should first obtain equation of the DC load line. Everybody knows from mathematics, every straight line is represented by equation. Yes or no? Y equal to mx plus c, or y minus y1 equal to m into x minus x1. Everybody knows this point. Every straight line is represented by equation. DC load line is a straight line, so there will be some equation for DC load line. How to obtain equation of the DC load line? To obtain equation of the DC load line, you should apply KVL in collector loop. Please copy this point. and I will take one circuit as an example. I will take one BJT circuit as an example, and through this circuit we will learn how we obtain DC load line and how it is useful. Okay, so let us take one circuit as an example. I hope everybody has copied it. I am taking this circuit as an example beta. It's a simple BJT circuit. For this BJT circuit, we will obtain equation of the DC load line. You can indicate here current IC. This is IC. Okay, this will be VCE. Then use KVL in the collector loop. This is called collector loop. Okay, you have to travel in this way. Ultimately, we want relation between IC and VCE. So you have to apply KVL in the collector loop. Collector loop. KVL. We get VCC is equal to ICRC plus VCE. This is called collector loop. You travel through collector and then emitter. This is your collector loop. If you travel through RB, that will be called base loop. Okay, if I travel in this way through RB and then base and then emitter, that will be called base loop. But when I travel through collector and then emitter, that will be called collector loop. So when you apply KVL in this collector loop, you will get VCC is equal to ICRC plus VCE. Now rearrange it. It will become ICRC is equal to minus VCE plus VCC, or it will be like IC is equal to minus 1 upon RC into VCE plus VCC divided by RC. This is some equation 1. Let us call it equation 1. That KVL I have written in this way. IC is equal to this much. Now remember, DC load line, it will be plotted on IC versus VCE graph. Here IC will be like y-axis and VCE will be x-axis. I have written it very clearly here. DC load line, it will be plotted on IC versus VCE graph. That IC will be y-axis and VCE will be x-axis. So in this way, if you look at the equation, that IC will be like y coordinate and VCE will be x coordinate. Okay, IC is like y coordinate and VCE will be x coordinate. So we can say this equation is in the form y equal to m into x plus c. Okay, it is in the form y equal to m into x plus c, and you know very well y equal to mx plus c. Y equal to mx plus c is the equation of straight line which has a slope m and a y-intercept c. Okay, that m will be slope and c will be y-intercept. So in this way, equation 1 is a straight line. It has a slope minus 1 by RC and it has a y-intercept VCC upon RC. This straight line will be called DC load line. Okay, this equation represents straight line having a slope minus 1 upon RC and a y-intercept VCC upon RC. So this straight line will be called DC load line. I hope it is understood. Here IC is a y coordinate, VC is a x coordinate. You can write this point here. equation 1 represents straight line having slope minus 1 upon RC and y-intercept VCC upon RC. Okay, it is called DC load line. It is called DC load line. Okay, this straight line, it will be called DC load line. For this circuit, for this particular BJT circuit, this is your DC load line equation. Milu John is asking what will be timing for second Saturday. I mean not tomorrow but the coming Saturday. But most likely it will be same 1 to 9. We will try to keep it 1 to 9. So much planning in advance. So this is the DC load line equation for this particular circuit. And we will now try to draw this line. For this straight line, y-intercept is VCC by RC. Okay. And you can also tell what will be x-intercept. You know from mathematics how to calculate x-intercept, y-intercept. We are able to tell y-intercept directly because it is in the form y equal to mx plus c. So this is your y-intercept. You can now tell me what will be x-intercept. To calculate x-intercept, we should put y equal to 0. And what is the meaning of y here? Y is nothing but IC. Put IC equal to 0, you will get x-intercept. When I substitute IC equal to 0, I will get VC equal to VCC. That VCC will be called x-intercept. Is it clear to all? To calculate x-intercept, you should substitute y equal to 0. And what is y here? IC. Put IC equal to 0. When I substitute IC equal to 0, I will get VC equal to VCC. Okay, you just substitute IC equal to 0, you will be getting VC equal to VCC. So VCC will be called x-intercept. X-intercept. I will write this also. X-intercept equal to VCC. And we obtain this by putting IC equal to 0. I have written it so that if you have a doubt, it should become clear. X-intercept is equal to VCC, and we get it by putting IC equal to 0. In this equation, you put IC equal to 0, you will be getting VC equal to VCC. Okay, that is called x-intercept. Once we know x-intercept, y-intercept, we can plot that straight line. Okay, if I know x-intercept, y-intercept, I can easily draw the straight line. Let me draw it in the next slide. IC versus VCE. Now this IC VCE graph, you will get it in the BJT characteristics. Maybe on Sunday when you go through the BJT EDC part, on Sunday you will be having EDC class where Sunil sir will teach you some BJT fundamentals which are a part of EDC syllabus. Okay, so there you will come across IC VCE graph. We call it BJT characteristics. This IC versus VCE graph, it will be in this way, beta. We call it BJT characteristics. This is obtained for different values of IB, IB3, IB2, IB1. Now no need to worry about these curves. These are called BJT characteristics. These graphs which I have drawn, they are called BJT characteristics. When we maintain IB constant at IB1, we get this bottom curve. When we maintain IB constant at IB2, we get this middle curve. And when IB constant at IB3, we get this top curve. This is called BJT characteristics. On this BJT characteristics, we plot DC load line. DC load line, it will be drawn on this IC versus VC graph. So let me now show the DC load line here. I will indicate here intercept, X intercept, Y intercept. That Y intercept was VCC upon RC, and X intercept, it is like VCC. Okay, for the DC load line, X intercept is VCC and Y intercept is VCC upon RC. Now you join these intercepts with a straight line. This is called DC load line. इसको हम ठीक से ड्रॉ कर लेंगे. It is a straight line. Okay. This straight line will be called DC load line. It has a negative slope. Slope is equal to minus 1 upon RC. Okay. So this is how we draw DC load line for a given BJT circuit. You should obtain equation of the DC load line, then you will come to know Y intercept, X intercept. Those intercepts you will show here and join those intercepts with a straight line, then that will give you your DC load line. It has a negative slope, minus 1 upon RC. Okay. And now let us say I know base current. Assume that in this circuit base current is some IB1. Let us assume that in this circuit base current is equal to IB1. Okay, just assume for the sake of understanding that base current is IB1. If base current is IB1, then the point where load line cuts this IB1 curve, okay, the point where load line is intersecting that IB1 curve, that point of intersection will be called DC operating point. This point of intersection, it will be called operating point. So I am introducing you to a new term, operating point. The point where load line is intersecting that IB1 curve, that point of intersection will be called operating point. We also call it quiescent point, Q point also. Okay, here I have assumed base current is IB1. If base current is IB1, then this point of intersection will become operating point. You can take this sentence also. For a given IB, comma, the point of intersection of BJT characteristics curve and DC load line is called operating point. Or quiescent point or Q point. Okay, for a given IB, the point of intersection of BJT characteristics curve and DC load line is called operating point or quiescent point or Q point. So remember this terminology: operating point, quiescent point, Q point. It is nothing but the point of intersection, the point where load line is intersecting that characteristics curve. If I assume base current is IB1, this will be operating point. And what will be coordinates of this operating point? For this operating point, coordinates are VCE and IC. X coordinate will be VCE and Y coordinate will be IC. That point of intersection, it will give you how much is the value of VCE and value of IC. You can write this point also. Coordinates of Q point are DC values of VCE and IC. Okay, you can underline this also. Coordinates of Q point are DC values of VCE and IC, and we normally show it in this way: Q VCE comma IC. Okay, that is how you represent any point in coordinate system. A x comma y. If there is a point A, its coordinate will be x comma y. So in the same way, Q point will be shown in this way: Q VCE comma IC. This is operating point for a BJT. In the exam, they will ask you question in this way: for the BJT circuit shown, find operating point. For the BJT circuit shown, calculate operating point. That operating point is nothing but VCE and IC. You should calculate DC value of VCE and IC. DC collector to emitter voltage and DC collector current. Those are the coordinates of Q point. So if I take base current as IB1, then this will be the operating point. Let us call it Q1. Okay, if I assume base current as IB1, this will be operating point Q1. Okay, if you want you can just write it as an example. If base current equal to IB1, then Q1 is operating point. Okay, the point where DC load line is intersecting that IB1 curve, that point of intersection is called operating point. This is just an example. Okay, if IB equal to IB1, then Q1 is operating point. And in case base current is IB2, let us say base current is IB2, then this will be operating point. This I will call Q2. If base current is IB3, this will be operating point. Let me call it Q3. Okay. If I assume base current is IB1, then operating point is Q1. If base current is IB2, then operating point is Q2. If base current is IB3, then operating point is Q3. So what I tell here is, when I change IB, if I let us say increasing IB from IB1 to IB2, then operating point will shift to Q2. If I increase base current to IB3, then operating point will shift to Q3. So what we should remember is, when base current is varied, operating point will shift on the load line. So in that way, load line can be called locus of operating point. Okay, when we change base current, operating point will keep moving on the load line. If I increase base current, operating point will move up. When I decrease base current, operating point will move down on the load line. So in that sense, load line is called locus of operating point. Okay, you can note down this point also. You can take it as a note. If IB is varied, then operating point will shift along load line. Operating point will shift along load line. Okay, and you can say hence load line is locus of operating point. Keep this terminology in the mind. It can come in your prelims ESC paper. Which of the following is true about DC load line? Which of the following is true about DC load line? You can say it is locus of operating point. Load line is locus of operating point. Okay, but I will give you my contact number, no problem. So everyone Is clear with these concepts? If there is any doubt, please ask. When base current is IB1, operating point will be Q1. When base current is IB2, operating point will be Q2. When base current is IB3, operating point will be Q3. Now, another important point that we should remember is when we design a BJT amplifier, okay, whenever we design a BJT amplifier, from that amplifier we expect distortion less output. Okay, distortion less output means output signal should be similar in shape to the input signal. Okay, if input is sinusoidal, output should be sinusoidal. If input is square wave, output should be square wave. From any BJT amplifier we expect that output should be distortion less. Okay, when I say distortion less, I mean output signal should have a shape similar to the input signal. So when we design a BJT amplifier and when we want distortion less output from that amplifier, then we should keep operating point at the center of load line. Okay, we have to design the amplifier such that operating point is at center of the load line. If you keep operating point at the center of load line, then it will help us in getting distortion less output. So this is another important point which every engineer should remember. Please note down this point. Very important sentence. To obtain distortion less output, from an amplifier comma operating point is kept at the center of load line, at the center of load line. Okay, to obtain distortionless output from an amplifier, operating point is kept at the center of load line, and such type of amplifier we call it class A amplifier. Class A amplifier, you can copy that also. Such amplifier is called class A amplifier. Okay, class A amplifier. Operating point at the center of load line, then we get distortion less output, and that type of amplifier will be called class A amplifier. Okay, there are other types of amplifiers also, class B, class C. Their operating point will be somewhere else. I will not go into those details here. Just remember that if operating point is at the center of load line, then that will be called class A amplifier. And I will try to give you some clarity about this. Okay, why operating point should be at the center. Let us say we have an amplifier in which operating point is at the center. This is load line, and assume that we have kept Q point at the center somewhere here. That Q point, its coordinates we can show VCEQ and ICQ. Okay, we can use suffix q here, VCEQ and ICQ. It will imply that these are coordinates of the Q point, VCEQ and ICQ. I'm assuming here operating point is at the center. Now this will be your ICQ, we call it quiescent collector current, and this will be VCEQ, quiescent collector to emitter voltage, VCEQ. This is VCEQ and this is ICQ. Now when we maintain Q point at the center, then this ICQ, it will be in the center of maximum and minimum collector current. Okay, this is VCC upon RC. When Q point is at the center, then this ICQ, it will be in the middle of maximum current and minimum current. Minimum collector current is 0 and maximum collector current is VCC upon RC. That y-intercept, it is nothing but maximum collector current, and 0 is minimum collector current. When we keep Q point at the center, then that ICQ, DC collector current, it will be in the middle of maximum current and minimum current, or you can say that ICQ is equidistant from maximum current and minimum current. I mean, this distance and this distance, they will be same. Quite obvious. Everybody in the class is a mathematician, right? When Q point is at the center, then this ICQ, it will be equidistant from maximum current and minimum current. This distance will be equal to this distance. And now when we design this type of amplifier, then what will happen is, when we give some input signal in this amplifier, let me assume that I apply some input signal. अब हम assume करेंगे कि हमने यहाँ पर कुछ input apply किया है. That input signal, it will be applied, let us say, at the base terminal. Just assume that we have applied some AC input signal, okay, to this amplifier. Let us say we are applying some AC input, and that AC input, let us say, it is a sinusoidal signal. Just assume that this Vs, it is some sinusoidal input. Whenever we form a BJT amplifier, to that amplifier we give some AC signal as a input. I am assuming here that AC input is sinusoidal. Now when we apply this AC input, then in the positive cycle, collector current will tend to increase. In the negative cycle, collector current will decrease. Okay, when we apply this type of AC input, that base current will vary like a sine wave. If base current varies like a sine wave, then collector current will also vary like a sine wave. If input is a triangular wave, then base current will vary like a triangular wave. Collector current also varies like a triangular wave. Here I am assuming this AC input is a sine wave. So when I apply some sine wave input at the base terminal, then base current will vary like a sine wave. Automatically collector current also varies like a sine wave. Now when Q point is at the center, then the advantage is, after application of AC input, collector current will be able to vary symmetrically. If I assume here that Q point is at the center, then after application of AC input, once we apply that sinusoidal AC input, then collector current will be able to vary symmetrically. It will increase and decrease by equal amount. Okay, because ICQ is in the center of maximum current and minimum current. So once we apply that AC input, that collector current will have a symmetrical variation. symmetrical variation means this variation and this variation, they will be equal. Okay, you are allowing the current to increase and decrease by equal amount. So this is called symmetrical variation. And if you allow current to vary symmetrically, it will help in getting distortion less output. Okay, input is sinusoidal, output will also be sinusoidal. So this is the advantage of keeping Q point at the center. You can draw this graph also, and you can take one more sentence about it. If Q point is at center of load line, then IC has symmetrical variation. Symmetrical variation when AC input is applied to amplifier. When AC input is applied to amplifier. And because of that symmetrical variation, we will achieve distortion-less output. If you want, you can underline this part. IC has symmetrical variation. I hope you understood the meaning. Symmetrical variation means this increase and decrease, they will be equal. I have assumed here input is sinusoidal, so collector current also varies like a sine wave, and it will be able to increase and decrease by equal amount. In the positive cycle of input, current will increase. In the negative cycle of input, current will decrease. If that input is a triangular wave, it will look like a triangular wave. If that input is a square wave, it will look like a square wave. And in all the cases, that variation will be symmetrical. Increase is equal to decrease. So this is the advantage of keeping Q point at the center. And I will take another situation here where I will keep Q point away from the center. Okay, let me take another example to give you better clarity. Let us say I have designed another amplifier, and this is the load line. Okay, and now let us assume that we have kept Q point away from the center, somewhere here. VCEQ, ICQ. Okay, assume that we have designed some other amplifier where Q point is away from the center. I have assumed Q point somewhere here. Now this will be your ICQ. This is ICQ, and here is VCEQ. Okay, this is your minimum current and this is maximum current. Now you can observe this DC collector current, it is not in the middle of maximum current and minimum current. When Q point is away from the center, then ICQ will be at an unequal distance from minimum current and maximum current. This distance is greater and this distance is less. Okay, from ICQ to 0 you have a less distance, and from ICQ to VCC upon RC you have a longer distance. Now to this amplifier, if I apply some AC input to this type of amplifier, if I give some AC input, then what will happen is, in the positive cycle current will have a proper variation, Okay, to this type of amplifier, if I give some sinusoidal AC input, then in the positive cycle current will have this much variation, but in the negative cycle current will decrease only up to 0. In the negative cycle current will decrease only up to 0. Current cannot become less than 0, so current will remain 0 for some time, then again it will vary like this. Okay, you will get this type of waveform in the collector current. When Q point is like away from the center, then in the positive cycle I have large variation, but in the negative cycle of input current will decrease only up to 0, and once current becomes 0, current cannot become less than 0. Negative collector current not possible. In a BJT circuit, collector current can decrease only up to 0. Yesterday we have seen when BJT goes into cutoff, IC will become 0, and negative collector current not possible. So in the negative cycle of input, when current becomes 0, it cannot decrease further, so current will remain 0 for some time. As a result, some part of input will be clipped, some part of signal will be lost. This is called clipping. Clipping will happen, waveform will get clipped. That clipping is considered as distortion. Okay, this portion of the signal will be lost. In the positive cycle your waveform is proper, but in the negative cycle some portion of the signal is clipped. We call it clipping. That clipping is nothing but distortion. Okay, so we may say okay, this type of clipping occurs. And that clipping is nothing but distortion. I mean, now that waveform is not similar to the input. Input we applied sinusoidal, but output will not be sinusoidal. Output will be some distorted waveform in this way. It is like a clipped sine wave. Output will be clipped sine wave. That means output is different in shape with respect to input. If output shape different from the input shape, then we say output is distorted. So this is what happens when Q point is away from the center. So let me write this point here. This is what you have to remember. If Q point is away from center of load line, away from center of load line, then variation in IC becomes non-symmetrical, full stop. Thus clipping or distortion occurs. Distortion occurs in output of amplifier. Okay, distortion occurs in output of amplifier. So this part you should keep in mind. Variation in IC becomes non-symmetrical. Collector current will have a non-symmetrical variation. Non-symmetrical means this variation and this variation, they will be like unequal. Okay, in the positive cycle current has a large variation, but in the negative cycle current will decrease only up to 0. So this is non-symmetrical variation. This increase is more, decrease is less. As a result, this clipping will happen. Clipping means cutting. Waveform is cut. Some part of waveform is cut. Okay, some part of waveform is clipped, and that is nothing but distortion. I hope everybody understood it. And I will give you sufficient time. You can copy these things. First you copy this part. First you copy this slide, then I will show you the next slide also. Okay, if this is taken, then please take next slide also. Copy these things carefully so that when you do revision later you should not get confusion. That's the reason I'm showing this slide once again. So whenever you want distortionless output from a BJT amplifier, you should keep Q point at the center of load line, and that type of amplifier will be called class A amplifier. Keep that in the mind. Okay, class A amplifier, operating point at the center of load line. It will give us undistorted output. Collector current will have symmetrical variation. But if Q point away from the center, then IC will have non-symmetrical variation. That increase and decrease, they will become unequal, and because of that clipping will happen. Here clipping is happening in the negative cycle. If Q point was at the top, if I keep Q point somewhere at the top, then clipping will happen in the positive cycle. Okay, here I have assumed Q point towards bottom end of the load line. Now clipping is in the negative cycle. But if I keep Q point maybe towards top of the load line, then clipping will happen in positive cycle. In either case there will be some clipping either in the positive cycle or in the negative cycle, and if the clipping occurs in the signal, it means output is distorted. Okay, I hope everybody has copied this also. Just let me know if you have completed copying this. we will try one question here. Let us try one simple question. Please take this question. Find the slope of DC load line. Find the slope of DC load line for circuit shown. You can take circuit number 1. Let us find slope of the DC load line for this particular circuit. Just take this question. We have to obtain here slope of the DC load line. So we will first obtain equation of the DC load line. You indicate here collector current IC. This will be your emitter current. That emitter current is actually IB plus IC, but practically IB will be much small as compared to IC. We have done so many questions earlier, and you can notice very clearly IB is much less than IC. Base current will be much small in comparison to collector current. So we can neglect IB in the calculation of DC load line. IE is actually IB plus IC. It can be approximated to IC under the assumption that IB much less than IC. Okay, practically this will be true always. Base current is much small in comparison to collector current. Normally base current will be in microampere and collector current will be in milliampere. In this BJT circuits, base current will be in microampere and collector current will be in milliampere. So we can do this approximation here. This you can show as VCE. And now just apply KVL here. KVL. We get VCC is equal to ICRC plus VCE plus IC into RE. Okay, I have approximated emitter current to collector current. I hope it is clear. From practical point of view, base current will be in microampere and collector current is in milliampere. So we can approximate IE to IC. Just apply KVL here, you will get this equation. Then you rearrange it. It will become IC into RC plus RE is equal to minus VCE plus VCC. Or I will get from here IC is equal to minus 1 divided by RC plus RE into VCE plus VCC divided by RC plus RE. This you can call as equation 1, and once again you notice it is in the form y equal to mx plus c. Okay, that IC is your y coordinate and VC is x coordinate. So it is in the form y equal to m into x plus c. So what will be slope here? Slope of the DC load line, it will be minus 1 divided by RC plus RE. Slope is equal to minus 1 divided by RC plus RE. This type of question can be asked for 1 mark in the GATE paper, or this kind of questions can come in your prelims ESC paper. For the BJT circuit shown below, find slope of DC load line. Minus 1 divided by RC plus RE. It's a negative slope beta, negative slope. Yes, I have got answers from Rishta, then Shashwat, Bidisha, and then Kushi. Yes, Abhinav. Minus 1 divided by RC plus RE. We will try one more circuit here. I hope you have understood this part. You can take one more circuit. Second one. This is another BJT circuit. This type of circuit, it will be called transformer coupled amplifier. This is another circuit for which we will find out slope. There is a transformer here, primary winding, secondary winding. This type of circuit is called transformer coupled amplifier. And for this circuit, we will find slope of the DC load line. We will apply KVL in this collector loop. You can show this as IC, collector current. That IC will flow through primary winding. Okay, collector current will flow through primary winding of the transformer. Then this you can show as VCE. Okay, and now you apply KVL in this loop. Just apply KVL here. This is your collector loop. Let me apply KVL. I will get VCC is equal to IC into 0 plus VCE. Okay, I have applied KVL here. I will get VCC equal to IC into 0 plus VCE. I'm assuming here that primary winding has 0 internal resistance. Okay, I'm assuming here winding as ideal. you know from networks, if a winding is ideal, its internal resistance will be 0. So we have assumed that primary winding has 0 internal resistance. This 0 is internal resistance of primary winding. Practically, a winding may have some small resistance. You know this concept from networks. Winding is nothing but you take some core material, on that core you will wind copper wire. Okay, that copper wire will be having some resistance, but ideally you can say its resistance is 0. तो हमने यहाँ पर assume किया है कि primary winding is ideal, so it will be having 0 internal resistance. So in this way I will get equation VC equal to VCC. VC equal to VCC. Now this VC equal to VCC, it is in the form X equal to K. Okay, VC equal to VCC, it is in the form X equal to K. Now everybody knows X equal to K. What is X equal to K? X equal to K is a vertical line. Okay, line parallel to y-axis. X equal to K is a line parallel to y-axis. So we can say DC load line is vertical. X equal to K is a vertical line. Let me write this point here. For transformer coupled amplifier, for transformer coupled amplifier, DC load line is vertical. This type of question appeared in prelims ESC paper. Which of the following is true about transformer coupled amplifier? And the true option was DC load line is vertical. So please remember this as a property. For transformer coupled amplifier, DC load line is vertical. Now what will be slope of a vertical line? Infinite. Infinite. It has infinite slope. Okay, vertical line has infinite slope, horizontal line has 0 slope. Everybody knows it. Vertical line means infinite slope, horizontal line means 0 slope. So for a transformer coupled amplifier, if you draw DC load line, it may look like this. Let us say this is your IC versus VCE plot. Then for a transformer coupled amplifier, DC load line will be in this way, vertical. It will cut the VC axis at VCC. Okay, this is how the DC load line will be for transformer coupled amplifier. It will cut the X axis at VCC. VC equal to VCC, X equal to K. So this was all about DC load line. I hope everybody understood these concepts. While finding DC load line, we should apply KVL in the collector loop. In collector loop, RB does not come. Bhavna, I hope your doubt is clear, beta. In this KVL, we don't get RB. RB will come when we apply KVL in the base loop. But DC load line, we obtain it from collector loop. So जब आप collector loop में KVL apply करेंगे, there will be no RB here. You have only VCC, primary winding and VCE. That primary winding we are assuming as ideal. Internal resistance will be 0. So in this KVL I don't get RB. DC load line will give relation between IC and VCE. Okay, remember that. And we obtain it by using KVL in collector loop. So we will conclude our today's class here. Okay, I will stop today. Tomorrow timings I have announced. Class will be from 1 to 9. Afternoon 1 o'clock to evening 9 o'clock. That is the schedule for tomorrow. 1 to 9. I will just write it here. This is the schedule for tomorrow. And some of you are asking my contact number. I will write that also. Okay, this is my contact number, 9849794795. If you have genuine doubts, you can send on this number. Okay, I have the same contact for WhatsApp as well as Telegram. I hope that is clear to all of you. So good night everyone. We will meet tomorrow at 1 o'clock. Thank you.